So we do all that work, we plug it into difference quotient, we have 2x plus h. Now, some of you, when I first brought up we use difference quotient for this, you remarked, wait, that's for secant line, right? And it is. But we can also use it for tangent line. Because remember, tangent line is what we get is that h value gets closer and closer to our starting value. In other words, as h is getting super, super small. In fact, really what we could do is we could write this then
h is 0?
As a limit problem.
Oh no.
This is just the limit as h is approaching 0 of 2x plus h. That's what the tangent slope actually is. And notice we hit a separate piece of the problem here. That's not just a continuation of the work, it's a new piece of work there. And so with this one, notice we can go ahead and just use direct substitution because we aren't dividing by 0 or anything like that. So if I put 0 in for h, the whole thing then just equals 2x. And so 2x then is an equation that tells us the slope of the tangent line, but we still don't know what x is, right? We do here.
-2.
Now that we have our equation, find the slope of the tangent line at each of those 3 points, please. And so for that first one, we should find the slope of the tangent line at -2, -3 is -4.
No, that's fine.
And so then once we plug in the other two the same way, plug the -4 in, plug the 1 in, we got tangent line slopes of -8 and 2. And so we're done. That's all we had to do for that. And finding that one equation, then let us apply it to all of these different points along the way. So reading through the problem here, we can see the general setup, but really the setup is just leading us to this equation. And we want to first find the average velocity. When we say average velocity, what are we really finding? Secant, yeah. The average velocity is the slope of the secant line. And then down here, we're going to be finding the instantaneous velocity. What's the instantaneous velocity then?
Tangent.
Yep, it's tangent. And so notice in this case, we need to find a bunch of secant line slopes, and we need to find a tangent line slope. So what will we use to find those?
Difference quotient.
Difference quotient, exactly. This is basically the same kind of problem, a little bit different, but it's the same basic problem as what we had in the last one, just in context. So go ahead and use difference quotient for this function and see where it takes you. Now, when I plugged in difference quotient, I went ahead and still used x and h in there. If you feel comfortable using t plus h, that would be even better. That would be a great idea and a good approach to do it. But x plus h is still okay if that was just a step too far. All right, so when we go ahead and boil down the difference quotient as far as we can on this one, we got 9.8x plus 4.9h. Now, do I want to go ahead and find the limit as h approaches 0 right now?
No.
No, not yet, because I need to use this formula here in order to go back to my problem. Because my problem starts with the average velocity, which is actually the secant line, which is what our 9.8x plus 4.9h gives us. All right, and so for this first problem, we want to know the average velocity between 3 seconds and 1 second. What am I plugging in for h on this one?
-2.
Maybe that one was too tricky. What are we plugging in for x? 3. Okay, yes, good. So we're going to go 9.8 times 3 plus 4.9 times, and it's not 2. It has to be -2, because remember that I'm starting at 3. And then it's, okay, what do I add to that to get to my desired number? And so that's why we'd have to add -2. We're going to left. You got to use the negative there.
It's around 9.
When you do that calculation, you should get an answer of 19.6 what?
Meters per second.
Meters per second, yes, because this one is actually in context. And you notice up here, it was talking about meters. And let's see, did it actually say, no, it didn't say seconds, but it is actually in seconds anytime you see that 4.9. If you've taken physics, you got that down already. But yes, it's meters per second. And then go ahead and continue that same process. Find the rest of our values if you haven't already. And so these are the values we end up getting when we plug those in. Now notice, when we plug them in though, the x part can stay the same. I don't have to keep changing that every single time. All I'm doing is changing the h value. All right, now for the last one, the instantaneous velocity at 3 seconds. In this case, what is h?
0.
0. Because instantaneous velocity basically is saying I'm looking for the limit as h is approaching 0 of my expression up there. And so I'm just left with 9.8x, and 9.8 times 3 gives us 29.4 meters per second.